Hi everyone, I'm Darshan from Department of Computer Science and Engineering, Sri Venkateswara College. Today in mathematics, we are going to discuss about ordinary differential equations for higher order. At first definition, an ordinary differential equation is a mathematical equation that describes the relationship between a function and its derivatives. Unlike partial differential equations, which involve multiple independent variables, ordinary differential equations only have one independent variable, usually denoted by x. The unknown in an ordinary differential equation is a function of this independent variable, and the equation relates the function itself and its derivatives rates of change to each other. Then let us know about the difference between ordinary differential equations and partial differential equations. At first, ordinary differential equations, one independent variable, usually denoted by x, derivatives are taken only with respect to a single independent variable. They model scenarios where change depends on just one factor, like the motion of a falling object or the temperature change in an heating rod. Then partial differential equation, which means two or more independent variables. Derivatives are taken with respect to multiple independent variables. They model phenomena where change varies with multiple factors like heat flow in a three-dimensional object or a wave propagation in a medium. Then let us see about examples of an higher order differential equation. At first, vibrating string. Imagine a taut string fixed at both ends. When plugged, it vibrates with its displacement from equilibrium position described by a function y of x comma t, where x is the position along the string and t is the time. You can see the equation where c is the wave speed. However, if we assume the string vibrates in only one direction, let us say vertically, we can separate the variables and obtain a fourth order ordinary differential equation for the time dependence of string's displacement at a specific point x. Then you can see a equation where L is the string length. Solving this equation with appropriate initial and boundary conditions reveals the frequencies and amplitudes of different harmonics present in the vibrations. Then a second, population growth. Consider a simplified model of population whose growth rate is proportional to its current size but limited by available resources. As you can see the equation where y of t represents the population at time t, comma a, b, and c are constants related to birth rate, death rate, and resource constraints respectively. Depending on the values of these constants, the equations can exhibit stable steady-state populations, oscillations, or even exponential growth and decline. These are just two examples showcasing the richness and diverse applications of higher-order differential equations. They capture complex dynamics in various fields from physics and engineering to biology and economics. Then this is the standard form of higher order differential equation where n is the order of the equation, highest derivative present. Then a and I are the constant coefficients. Y to the power I represents the ith derivative of the unknown function y of x. F of x is the forcing term right hand side, which can be any function of x. Then let us see methods of solving higher order differential equations. At first, analytical method, in which method of undetermined coefficients. This technique shines when the forcing term in the non-homogeneous ODE is as a well-defined form. We assume a particular solution with the same form as the forcing term, determine its unknown coefficients by equating terms, and voila, the solution emerges. Then comes variation of parameters. This method is like wearing a mathematical invisibility cloak, allowing us to sneakily modify the general solutions of the homogeneous equation to fit the non-homogeneous case. We introduce unknown parameters in the fundamental solutions and solve for them to obtain a particular solution tailored to forcing them. Then reduction of order. For special cases of second order equations, if one solution is known, this unique transforms the equation into a first order one, often simplifying the solution process. It's like finding a shortcut through the mathematical maze by leveraging existing knowledge. The second one is numerical methods. Numerical methods which include Euler's method. This workhorse technique is the simplest numerical approach, approximating the solution step by step on a discrete grid. While not the most accurate, it provides a valuable initial glimpse into the behavior of the solution and serves a foundation for more sophisticated methods. Then let us see about Laplace transform. Higher order differential equations can sometimes feel like intricate puzzles locked away in time, but fear not, for the enigmatic Laplace transform emerge as a powerful tool offering a time-traveling bridge to their solutions. Then let us see about the art of transformation, in which the imagine the higher order differential equation as a complex landscape of derivatives and functions. The Laplace transforms acts as a magical telescope, transforming this landscape into a new domain where the equation takes on a simpler, often algebraic form. By working in this transform domain, we can readily find the solution and then use this inverse Laplace transform to journey back to the original time domain, revealing the answers we seek. Then let us see some of the benefits of Laplace transform. At first, simplicity. Complex derivatives vanish, replaced by an algebraic manipulations. Then comes versatility, applicable to diverse linear ODEs with various forcing terms. Then initial conditions incorporations, easily incorporated into the transformed equation. Then these are the some of the examples of real world problems. Higher order differential equations aren't just elegant mathematical expressions. They can bring life into diverse real world phenomena. Here are some examples. At first, vibrations, heat flow, population dynamics, electrical circuits, and chemical reactions. Then, conclusion, ordinary differential equations aren't just intimidating strings of symbols, they are the hidden conductors orchestrating the symphony of reality in diverse fields. Their ability to capture change and its interstices make them indispensable tools for scientists, engineers, and economists alike. Imagine we cannot even imagine a world without ODEs, which means ordinary differential equations. At first, bridge even couldn't stand tall. Engineers wouldn't be able to model the vibrations and stresses bridges endure, potentially putting their safety at risk. Then medicines wouldn't reach their targets. Without the equations governing drug diffusion and interaction, effective drug delivery and disease treatment would be a distant dream. Then rockets wouldn't have soared. The intricate dance of thrust and gravity wouldn't be understood, hindering our celestial explorations. Thank you.